Next very important question, let us see how to drive large capacitive loads. What do you mean by driving large capacitive loads? That is, how much time is required to charge and discharge a capacitance, and if it is a arriving or if it is showing at the load. The time taken for charging and discharging of these capacitive loads will result in a huge delay. Hence, we have to ensure that the time taken for the charging and discharging of these capacitive loads will be as much less as possible. So, then what are the different ways of ensuring that the time taken or the delay of driving your large capacitive load is less? We have different methods. The first method is cascaded inverters are used as drivers. Second method is I am going to use BiCMOS drivers. Third is I may use what is called as super buffers. These are the three ways in which I can reduce delay in charging the large capacitive loads. Let us go one by one. First, let us take the cascaded inverters as drivers. Okay. So, what we do here is, instead of having one driver, a CMOS inverter which is huge in size, okay, which is very huge in size, what we are going to do is we are going to split it into some n number of stages, wherein your first stage will be a smaller one, and then second stage will be a bit bigger than the previous one, third stage, like this the stages go on, and the sizes of the inverters also increases as you proceed forward in driving your large capacitive loads. This is your CL, this is your ground. What will be the ratio of this? This is a CMOS inverter. This will be, pull up will be 4:1, pull down will be 1:1, because we don't want the rise time and fall time to vary. We want them to be equal, hence I am increasing the size of my PMOS. There it is 4.1. Next will be 4:F, and this is 1:F. Next stage will be 4:F square, 1:F square. What is it you are seeing? As you proceed forward, the size increases by a factor called F square, then it will be F cube, like that, where F is called the width factor. Okay, so it increases by the width factor. And with large F, more or the sizes of the transistor, large F, my stages, N is nothing but the stages. The number of stages decreases, but as you proceed with the larger F, the delay increases. Hence, I have to ensure how many stages should I be using to see that the delay will reduce. Okay. So, for a 4:1 NMOS inverter, a standard delay will be for 1 to 0, or let me say increased V in 0 to 1 transition, it is F into tau, and if it is 1 to 0 transition, this will be 4 F into tau. So, total will be 5 F tau will be the delay of your NMOS inverter. Similarly, if it is a CMOS inverter, this is a standard what is assumed, it will be 7 tau. Okay. So, now let us assume a parameter called y, that is given by CL divided by square Cg, that is equal to F to the power n. Let us take logarithms both sides. We get natural log of y is equal to n into natural log of f, or from this n is equal to natural log of y divided by natural log of f. Okay. If we say the number of stages is even, if n is even, then total delay will be equal to n by 2 times 5 f tau if it is for your NMOS. Same way, if it is for PMOS, it will be n by 2 7 f tau if it is a CMOS, or for all cases for all cases. I can say delay is proportional to n f tau, that is natural log of y divided by natural log of, I am substituting for n, f into tau. This will be the delay, wherein this clearly says that the delay is directly proportional to number of stages. As the number of stages increases, my delay increases, and frequency also is your f will also play a very it is a factor here, it is not frequency actually. This also plays a very important, and you have your delay unit tau, which depends on the sheet capacitance, sheet resistance, and your gate capacitance, which is directly proportional to your delay.